we've covered the first law of thermodynamics for a closed system undergoing a process. Now, a special type of process is one which might be made up of a number of processes, but ultimately the beginning state of the special process called a cycle ends up right back where it started from. We call that a cycle. So let's get started looking at a way to express the first law of thermodynamics for a cycle. This is going to be kind of involved, so I kind of like to give you a roadmap of where we're headed in this video. First is we're going to do that recap of that special process, of that special type of process we call a cycle. I'm going to remind you of that. Going to take you through an exercise where we visualize W net, the net work out for a cycle. And then we're going to go through an exercise looking at the energy change for a cycle, delta E. We're going to talk about dealing with heat transfer for a cycle. And that's going to deal, once we've covered those, going to be able to develop a statement of the first law of thermodynamics for a cycle, a system undergoing a cycle. And then I'm going to review with you a way to depict by hand drawn what I call a cycle schematic. And it's something that my thermodynamics professors taught me to do, and I embraced it, and I have used this cycle schematic for years throughout graduate school and then throughout my engineering practice up through retirement. So the first thing let's do is I'd like to take you through an exercise where we visualize the network done by a cycle. And in a green text, but it's green because I've copied it and pasted it from a previous video presentation. It says a cycle, keyword cycle, consists of any number of processes, any number. I'm thinking at least two processes or more, where the final state returns exactly back to the initial state. It's simple as that. And I've taken a screenshot of a slide that I've drawn before, a recycled slide from all the way back to Chapter 1 when we were talking about processes. Now, and here it is, and I'll remind you that what we're going to propose is that here's 1, 2, 3, 4, 5 processes. And all of these processes are going to be considered quasi-equilibrium processes. In other words, now, each process does not have to be a straight linear line like I've shown here. I'm just showing them as straight lines just due to laziness, but you could make these little curved lines in any way you wish to do it. But recognize that we need to be able to, each process needs to be described by an analytical expression or a function. Okay, that's the nature of what quasi-equilibrium means. At all points within any process, let's say 2 to 3, all of these points are in equilibrium. So in other words, basically things are happening rather slowly. And remember, the depiction of our closed system is over here, the tried and true piston and cylinder. And so the closed system is contained within this dashed line. Okay. And let's see, what else do we remember? We showed this process on a pressure volume diagram that had some advantages. Can you think of one of the advantages of drawing a pressure volume diagram for a closed system? I can. I'd say one of the big advantages is for a quasi-equilibrium process, you can visualize the work so that you can graphically visualize the work, the integral of P dV, the area under the curve. So let's see what we can learn if we start dissecting this. So I've convinced you that this is a cycle because we're starting at state 1 and we're ending back at state 1. It's a cycle. let's look at process 1 to 2 first. And so since we've got quasi-equilibrium closed system, do you see that sort of this red cross-hatched area? That's a graphical representation of the work out from 1 to 2. Let's see, the work out, that's a negative number, isn't it? Because we're integrating from right to left. And so work is required for this particular process. That's why I've shown it in red. But it's easy for the straight line process. It's a trapezoid. It's really easy. It would be easy to compute that number numerically, wouldn't it? Let's go to 2 to 3. Process 2 to 3. Now we're going from left to right. We're looking at the area under the curve. So I've cross-hatched that out as green. Green, workout positive. And do you see that you can't see the green underneath the red? So the red and the green overlap in this region here. That's going to be important, so please do recognize that. But it's easy, and you see that, well, we've got another trapezoid. It would be easy to calculate the work from 2 to 3 for this straight line process. Let's go on to 3 to 4. Same drill. Wow, we've got more positive work out. That's good. If we're looking for work out, to say to lift a weight, we're doing great. 3 to 4, wow, we've got positive, more green, positive, integrating right to left, integrating left to right, positive result, integral PDV. What does 4 to 5 look like? Well, 4 to 5, that's going to be a negative amount of work because we're integrating right to left. And do you see that the red is overlapping the green from 3 to 4? Okay, that's going to be important to recognize. Let's complete the cycle. 5 to 1. Well, work out. We're going right to left. Visually, I see what I've got. Again, easy to compute. And so do you see that the red is overlapping the greens that went all the way down to P equals 0. Okay. So that's an important thing to recognize. But another thing to recognize is I've just scoped out an area of green. And that represents the net work done by all the processes add together. So this green is a representation of the net work of the cycle. Okay, so here's some conclusions over that little exercise. So the area inside the cycle, see how the cycle scopes out a certain area, doesn't it? In the PV diagram. So the area inside that cycle reflects W net. Now you've got a visual look at the net work. Now here's another thing that particularly my first quarter thermodynamics professor drilled into our heads. When you've got a cycle and you have net work positive, show a clockwise arrow. Do you see what? Look how the arrows of the processes here suggest which way you need to draw your block arrow, right? For this one, clockwise. Now, if we had gone the other way, if I had come up with a different and said, I've got a cycle that I'm going to describe as going 1, 5, 4, 3, 2, 1. See, I'm going to do that again. Different proposal, 1, 5, 4, 3, 2, 1. I'd go the other way, right? So what's inside that cycle would have been red for that example, right? Because you go through that same mental exercise, draw things red and green, you're going to have some reds, some greens, and that would all be red. And then we'd look at the arrows and we would draw our block arrow in the counterclockwise direction. And that, for that example, that would tell us that our net work is negative. In other words, net work would be required to complete the cycle. But what we've got here on the screen is here, clockwise arrow, W net greater than 0, net work is produced by the cycle. This is called a power cycle. Net work is positive. Really cool result. So I declare you an expert in visualizing the net work done by a cycle. Now let's look at the energy change delta U. So, for our little example problem, let's say we're going to our piston and cylinder are stationary. They're not moving. So potential energy isn't changing. Kinetic energy change is not changing whatsoever because there is no kinetic energy. All right, so let's just say that. And all we're interested in is the energy change delta U, delta U. Now, you know what the answer is going to be before we go through the exercise because a cycle begins and ends at the same state. So since U is a property, delta U is 0. So we know what the answer is going to be, but I want to drag you through something to show you something a little different. Here's what I want to do. So I've shown a little postage stamp of our cycle over here on the top right. I've written down the first law of thermodynamics for a closed system undergoing a process. Got it? So that's what I'm writing up here, and I'm striking out delta KE and delta PE for our example. All right. So let's write down, we've got 1, 2, 3, 4, 5 processes. Let's write down the first law for each of those processes, and let's be careful about our nomenclature, the way we label our heats and works. And this has got some value to it. Notice here, process 1 to 2, you see that I'm not just writing down QN because I've got lots of QNs. I've got 5 different ones, and I've got 5 different workouts. So I've got to be clever as an engineer and kind of work through my nomenclature so that everybody will understand what I'm doing, including myself when I go back and look at this again in a few weeks. So I'm going to call this QN from 1 to 2 minus the work out from 1 to 2 equals delta U. That's U2 minus U1. And I'm going to do it again for process 2 to 3. So this time I've got QN from 2 to 3, not just QN, minus W out from 2 to 3 equals delta U. Well, this time it's U3 minus U2, and on and on and on. I'm sure you're glad I'm not going to read all 5 processes to you like that. But now let's see do we see a trend? Well, I do. I see a U2 here and then a minus U2 there. And so that's why I crossed out those two. Oh, I'm sorry. We're going to add up all the columns now. So what we're going to do is do like an accounting problem. We've got all 5 processes tabulated. We're going to do a grand total on each of these columns. That's what I wanted to say. So let's look at the right-hand side. Do you see how these U2s are canceling? U3s are canceling. U4s are canceling. U5 are canceling. And look at the U1. I've got a plus here and a minus up there. Those are canceling too. And so sure enough, we're going to get the result that we knew we were going to get all along is that delta U, or in other words, for our example, delta E is 0 for the cycle. We're going to cycle. Okay. I took you through that exercise. Do you see that if we add all of these up, we get W net because we've got a visualization up here in the top right of what W net is, and it's simply adding up all those little workouts. So we got W net. Now, so one thing I want to discuss a little bit. I want to be a little loosey-goosey on this, and I'm going to bet the textbook is a little better in describing this than I will be, but I'm going to give it my best. It turns out that when we get better in Chapter 3 at identifying ways to compute, the ways to quantify delta U, and we can already get W outs, right? Integral PDV. It's going to take Chapter 3 to go in and numerically identify what all these capital U's are. So when we get to that point, I'm going to tell you that some of these QNs are going to be greater than 0. And some of these QNs are going to be less than 0. So right now, all I'm going to do is plop down a box, some greater than 0 and some less than 0. You just kind of go with me on that. So let's see where we go with that. We're headed towards a statement of the first law for a cycle. I've got a little nomenclature, so what I'm going to do is pull a little bit of a trick and introduce a couple of new variables. So the heat transfers that I got from my, let's say, calculations that were positive, I'm going to add all those up, and I'm going to call those QH. And all of the heat transfers, QNs, that turned out to be negative numbers, I'm just going to add those up. And I'm going to call those QL with the minus sign to reflect that I got a negative number. There's my minus sign to reflect I got a negative number. Okay. And another, okay, so anyway, that's turning my sort of light yellow box into something mathematical. And then another thing I'm going to do is I'm going to take my W net and add it to each side, or in other words, slip it over to the right-hand side. So I've got QH minus QL equals W net. So can you go along with me on that? So so I want to continue this thought on, but you see, I pulled a little trick. I had to do a word trick of saying out of those 5 QNs, some of them turned out to be positive numbers, and some of them turned out to be negative numbers. Okay, so that was the idea there. So I'm going to split those out. If you can hang with me on that, then it turns out that little mathematical equation turns out to be a statement of the first law and energy balance for a system operating in a cycle. So see my green text box, statement of the first law for a system operating in a cycle, and there it is. Here is our functional description of the first law of thermodynamics for a system operating in a cycle. QH minus QL equals W net. Simple as that. Incredibly simple looking. Wow. Now I'm going to back up a little bit. I will certainly encourage you to go to your textbook, to have a discussion in class, to maybe ask any clarifying questions to your instructor, because I'm going to jump down and go backwards to a better, more formal mathematical description of this simplified description of the first law. And here it is. Here's the integral sign with a circle in it, an integral sign with a circle in it. And then what you're integrating is, it's not like dQn, it's del Qn and del W out. And so here's what this says in words. So the integral sign with that circle in it means that you have to do an integral around the entire cycle, around that entire cycle. You perform the integral around the entire cycle, all the processes that make up that cycle. That's what the cyclic integral is. So the wording of this fundamental is, it says the cyclic integral of heat, that's this, equals the cyclic integral of work. And if you choose to go to graduate school and take graduate level thermodynamics, this is where you will start in terms of your cycle analysis. So this is a little bit more of a better mathematical explanation or description or fundamental of the first law. This is a working statement of the first law for us. My professors, all of my professors, thermo professors, your class was busted up into a number of quarters when I was a student. So that's why I talk about my thermo professors. I had different professors in different quarters, and you're on semesters now. But all of my professors, especially my first one, said, so we're talking about a cycle. This is a schematic drawing that simplifies what we're talking about. And I want to pass this on to you all. It is somewhat covered in your textbook, but I strongly suggest you adopt this practice. And I'm going to talk more about what this means here in just a minute. But the cycle is contained within this black box, and a little bit more about that. But this would be called a schematic for a power cycle, also known as a heat engine. When you go to graduate school, you're going to call this a heat engine. But for right now, let's just call it a power cycle. And the reason it's called a power cycle is that W net, the net work, is a positive number. The net work is a positive number. You're making net work. You're able to lift a weight with this cycle. You're able to lift a weight outside of the closed system. Okay, I'd like to take a couple of slides to dissect this really valuable schematic of a system operating in a cycle. Okay, here's my statement of the first law, which is going to help us talk about the schematic. Do you know, it says QH minus QL equals W net. The first thing I should show, and I don't have anything written down, notice how I've got arrows, thick black arrows. How many do I have flowing into this black box? Oh, let me go to the left first. Getting ahead of myself. This piston and cylinder, here's our closed system, piston and cylinder. What I want to suggest is that you visualize taking this thing and putting it inside this black box. And in your mind, you're thinking that this thing is going through a number of processes, multi-processes, to complete the cycle, to start and complete the cycle. So there's a thing or things inside here. There's equipment inside here that's going through a cycle, similar to our example problem. Thus, inside this black box, I've shown a clockwise arrow here. So here's a text box. The clockwise arrow signals W net is greater than 0. Now let's look at our arrows going into and out of our black box. How many arrows are going in? 1. What's coming out? What's coming out is net work and also heat transfers coming out. Okay. So do you notice that visually, this QH minus QL, let's say, what if I move this QL to the right-hand side? You see I have QH equals W net plus QL. You see that? QH equals W net plus QL. Look at that. Q at left-hand side. That would be what's coming in. And then W net plus QL, that's what's coming out. And so visually, the statement of the first law, this is why it's been so valuable for me. That's why it's paid off for me. I thank my especially first quarter thermodynamics professor, Dr. Fury, for giving us this visual. And that is that these arrows have to balance out. Look, if this is 5 units and this is 4 units, you can immediately see what this needs to be. 1 unit. So if you've got 5 units coming in and 4 units coming out here, to satisfy the first law, you got to have 1 unit coming out there. And it works other ways too, right? So example, if you know that you've got, let's say, 10 units coming in here, 10 coming in, and 2 going out, 10 units in, 2 out. What's W net? 8, just by subtraction. And I was able to sail through Dr. Fury's quizzes because he would give us these numbers tabulated. He wouldn't give us the sketch. He'd give us these numbers tabulated, and we had to figure out the unknown one. And by working with this sketch, the schematic that he did not provide to us, I was able to sail through quizzes that were associated with that. All right, so that's my commercial for getting familiar with getting comfortable with drawing this sketch. Haven't said anything about TH and TL yet. Let's see, I did say a lot about QH and QL, didn't I? So do recognize that this QH going in, that is heat transfer that's added during the cycle. This QL down here that's depicted going out, well, just recognize that that would represent heat transfers that turned out to be negative in your calculations. In other words, heat transfers that were rejected from the closed system. So I'm playing a little bit loose with the pluses and minuses on my QNs, but the schematic and the arrows, I think, make up for it. So let's move ahead. So do recognize the arrow nature of inputs and outputs of forms of energy in my black box where the mechanical engineering equipment is located. The block arrow tells you clockwise, net work is positive. Okay, now for these gray TH and TL boxes. This TH represents a high temperature heat source, what we call a reservoir. We call it a heat reservoir in graduate school. high temperature heat reservoir. The reason we have that is, do you remember that, when we were talking about the definition of heat transfer, heat just doesn't appear out of nowhere, does it? Heat can only flow from hot to cold on its own. On its own, heat can only flow from hot to cold. And so we have to have some heat source that's hotter than the hottest temperature in our equipment. So that's why we have TH, is we need to get our heat transfer in from somewhere. And this is where we're getting, this is the schematically, we're getting it from some high temperature heat source. Let's go down to the TL. Well, it's the same idea, but we have to reject heat. We have to reject heat. In some of those processes, we end up having to reject some heat. You have to get rid of heat. Well, what's the only way we can get rid of heat? We can't just send it off into Never Never Land. We've got to send it to a place that is colder or cooler than where we're at. And so thus, we've got to find some low temperature reservoir that we call a heat sink, low temperature reservoir in graduate school. We have to find a heat sink to send that rejected heat to. And so that kind of completes the description of this extraordinarily valuable cycle schematic diagram. So this is simply putting it all together, of all of those little notes that I tried to step you through. I hope that helps, and I do really, really want to encourage you to think about adopting this sort of hand-drawn sketch. Doesn't have to be a work of art. Hand-drawn sketch when you're dealing with homework or quiz or test problems that involve a cycle. Wow, so we have actually reached the end of this video as well. Let's say, what are the most important parts? It was sort of a busy video, working through a lot of things, okay? So let's hit the high points. We've got two statements of the first law of thermodynamics for a system operating in a cycle. The top one is the most important because it is the one that is actionable for you in your engineering problem solving. QH minus QL equals W net. So there's a lot of things you have to understand about it, and it only applies to a system operating in a cycle. It's not a formula that you can just use on everything. On the mathematical side, certainly where you will start in graduate school, it says the cyclic integral of heat in equals the cyclic integral of work out. And the last thing is that I really want to provide a strong commercial and encourage you to think about what's behind this power cycle schematic. You don't have to memorize it. Just see if you can think about generating it on your own, what's behind it, and why might it be valuable. For me, it's valuable because I can plop down numbers on two of these arrows, and I can immediately determine the value of the third arrow. All I need, you give me two of those numbers, I'll give you the third one. Okay. Now, it's it's all schematically, it's the same as plugging and chugging through this formula. But I got to tell you, if you're anything like me as a student, I benefit a lot by seeing things and seeing stuff down on paper and visually seeing numbers and being able to balance things out with my eyes more than simply blindly following an equation. So I hope that helps. I hope that sort of gets you interested in thinking about drawing that cycle schematic to help you out. And I want to have one last video where I recap chapter 2. In chapter 2, a little tougher than chapter 1. So maybe some homework problems that are a little tougher because they're starting to involve the first law to a small extent. I can assure you that it gets tougher. Once we get into chapter 3, these problems get a lot harder than in chapter 2. So I want to recap what we covered. We covered a lot of material in chapter 2, and so I want to recap that for you. So please do at least breeze through the recap to try to put a lot of these fundamentals that we covered in Chapter 2, cement them in your mind.